It can be baffling when large systems, companies, economies, even ecosystems, seem to overreact, sometimes violently, to what look like very small events. But what if these responses aren't random at all? Today, we're going to explain the hidden logic behind why systems overreact.
See, most of us operate with a pretty simple and linear mental model of the world. We instinctively expect that causes will be proportional to their effects.
A small push should result in a small movement. A moderate effort should get you a moderate result. This idea of proportionality just feels right. It's deeply intuitive.
And yet, when we look at the complex systems that actually govern our world, we consistently see something different. We see minor, almost insignificant events triggering massive, completely disproportionate outcomes. The reaction seems to have no rational connection to the action. It defies our linear expectations.
Well, this isn't random. It turns out to be a predictable, structural property of how these systems behave. So what explains this gap? What's the hidden mechanism that allows a tiny trigger to produce a system-wide transformation?
To find the answer, we have to start with a system's most fundamental purpose. And for most complex systems, that purpose is simply to maintain stability.
So, what is stability? It's really just the ability of a system to hold on to its core functions and its structure, even when it's being pushed around by external disturbances. It's a drive towards equilibrium, its default state of being.
A really powerful way to visualize this is to imagine a ball resting at the bottom of a valley. You can give it a small push, and it might move up the sides, but gravity is always going to pull it right back down to its original, stable position in the center.
Now, to make this a little more concrete, let's introduce an abstract component that we'll call a stability regulator. Its entire job, its only function, is to keep some key performance level, that could be quality or output or safety, within a desired optimal range.
For example, think about a content platform. It might use a moderation process, that's its stability regulator, to maintain a consistent level of quality. If you're a user looking from the outside, the system appears perfectly balanced. It's functioning exactly as it's supposed to. Everything seems fine.
But how does that regulation actually happen? Well, the core mechanism that governs both stability and instability is something called the feedback loop. The stability regulator's main tool is what's known as a negative feedback loop. So when some variable deviates from where it should be, this loop kicks in and triggers a response that counteracts that deviation. It pulls the system back toward its target. Its whole job is to dampen change.
Now, in complete contrast, you have the positive feedback loop. This one is self-reinforcing. Here, a deviation triggers a response that actually amplifies the initial change, pushing the system further and further away from where it started. Its function is to accelerate change.
The logic is actually pretty straightforward. A stabilizing loop, the negative one, says if A increases, we'll do B to make A decrease. But a reinforcing loop, the positive one, says if A increases, we'll do B to make A increase even more. One corrects, the other one cascades. So let's go back to our platform example. Its regulator is using negative feedback. If the amount of low-quality content starts to rise, the moderation system simply works harder to filter it out, which brings the platform back to its target quality level. The system self-corrects. And again, from the outside, it looks perfectly healthy. Now, this model of constant, perfect correction makes the system seem almost infinitely resilient. It suggests that any deviation can be managed, but that is only part of the structure. And this brings us to a much deeper layer. You see, stability is not a static property. A system's capacity to absorb shock, what we call its resilience, can actually degrade over time, often completely invisibly. Let's go back to our metaphor of the ball in the valley. A healthy system starts out with high resilience. The valley of stability is deep, its sides are steep. This means it can absorb pretty significant disturbances and still easily roll back to its central, stable state. But what happens when that system is put under sustained, chronic pressure? It has to constantly expend energy and resources just to keep correcting itself. And this continuous effort slowly, invisibly, erodes its buffer capacity. The walls of that valley start to become shallower. Over time, that valley can become almost flat. Now, the system may still appear perfectly stable. The ball is still sitting at the bottom, but its resilience is gone. It has lost its ability to manage disturbances. It has become critically fragile. And in our platform example, this means the moderation system is now working at 100% capacity just to maintain the status quo.
The quality level still appears normal to the outside world, but the regulator has absolutely no reserve capacity left. The system's buffer against any kind of sudden surge has been completely used up.
This hidden fragility is what sets the stage for the final act. Because now, all that's required is just one more small push on a system that has no capacity left to absorb it.
This moment is the tipping point. It's a critical threshold where one more small stressor is enough to force the entire system to reorganize, often abruptly and irreversibly, into a completely new configuration.
That final, tiny push is just enough to knock the ball out of its dangerously shallow valley. But this time, instead of returning, it just keeps rolling until it finds a new, different valley, a new, alternative, stable state. This is the disproportionate reaction we see from the outside.
So what we perceive as a sudden, massive overreaction isn't a system error. It's not a random failure. It is the logical, predictable transition of a fragile system from one stable state to another. The real cause wasn't the final trigger, but the slow, invisible erosion of resilience that happened long, long before it.